In this video, I'm going to show the image of why we need a TX multimode driver in the SerDes system. The first SerDes system limitation will be the supply voltage versus the output swing. In the high-speed SerDes design, the device of the output driver will be a cold or low-voltage device. In addition, the SerDes system will leverage all the advanced technologies scaling benefits like low power, high speed, and low area. For example, the CVF power scales well for digital circuits to achieve a low power while the supply voltage is reduced to below 1 volt or even 0.75 volt in a 5nm FinFET technology. Unfortunately, the reduced supply voltage may have a fundamental constraint on the ergo circuit's headroom. Also, a high-speed SerDes will need to accommodate for high loads of up to 30 dB or even 36 dB at the next rate. Therefore, a 1 volt output swing is necessary and specified in some electrical specifications. Let's look at the current driver's case study about the design challenges from a low supply voltage and high output swing requirements. For the current driver, we know that both the current source and input differential pair must stay in the saturation range for a good current source and amplifier purpose, respectively. Therefore, both VDS voltage must be greater than the VDSA voltage, which would limit the output swing if the supply VDD is reduced here. If that's the case, what can we do? Think about the trial region images for 5 seconds. Right, the voltage mode driver may help. As we discussed in the YTX driver video, the output swing comes from the series voltage oversupply. Therefore, those CMOS switches should be in the trial region and have as little voltage drop VDS as possible. Ideally, the voltage drop at the active device or CMOS switches would be 0. So it's possible to achieve a big output swing and low supply VDD at the same time compared to the current mode driver. But we need impedance match to maintain good signal integrity. So the swing will be half of the swing image here, and the swing may be still limited if the supply voltage is too small. For the impedance match purpose, the revised image will be 100 ohm differential termination at the RX input for the far end matching. For the driver near end matching, the switches or inverters must be properly sized such that their large signal equivalent turn-on resistance M13 R on N and M24 R on P are equal to 50 ohm respectively. So the driver's output swing or the RX input swing will be halfway through the matching voltage divider. As we mentioned, if the supply is 1 volt, that's sufficiently large for 1 volt peak-to-peak differential output swing. But if the supply drops to 0.75 volt, that might still be challenging to achieve a 1 volt peak-to-peak differential output swing. In addition to a supply and swing constraint, the power will be a critical factor in a SerDes system, especially the TX driver's power. Why? Think about the signal power images for 5 seconds. Correct. The delivered output power will be a square of the voltage swing divided by the output load resistance. Since the output swing may need 1 volt, such a high swing under low impedance 50 ohm media, the power will be dominated by the output driver compared to other ergo circuitry with a moderate swing and a high impedance condition. if we could implement a power-efficient driver, the whole SerDes power can be very competitive, right? But how? Exploring both current mode and voltage mode driver may show you the power images further. The current mode driver's current versus output swing image is shown here. The differential swing of a large 1 or 0 is driven by 1/4 current times differential resistance 2R. Therefore, the total current would be the differential peak-to-peak differential divided by single resistance R. Then, the power would be the supply voltage VDD times the total current I. Is this low enough? Of course not. Let's check the voltage mode driver current versus output swing image under the impedance matching. The differential swing of a large 1 or 0 is driven by the voltage divider, which is half of the source voltage or supply voltage. Therefore, the total current would be the differential peak-to-peak differential swing divided by 4 resistance 4R. Again, the power would be the supply voltage VDD times the total current I. To compare the power fairly between the voltage mode and current mode drivers, both supply VDD is the same, and the current or power of the voltage mode driver is only 1/4 of the current mode driver, owing to the voltage mode driver's extremely low power. More and more high-speed SerDes apply the voltage mode driver recently, not only for NRZ SerDes, but also a painful SerDes. Here are the summarized images of why you need a voltage mode output driver in the SerDes system. In a SerDes system, there is a trade-off limitation between the supply voltage and output swing in a current mode driver. Since the CMO, both current source and input differential pair must stay in the saturation region. Both VDS voltage drop must be greater than the device VDS set voltage, which will limit output swing under a low supply voltage. For the voltage mode driver, that's 0 or very little voltage VDS drop in the active switch device, owing to its series of low impedance features. So, the voltage mode driver's series impedance matching may people also call it source series terminated SST driver. In addition to the supply or swing limitation, the low power is very demanding in SerDes. Because of the high output swing and low impedance at the TX driver, reducing the TX power will provide the best design return in power. Lastly, both the current mode and voltage mode drivers' current versus output swing image shows the current or power of the voltage mode driver is only 1/4 of the current mode driver ideally. The voltage mode driver's extreme low power benefit will push recent high-speed NRZ or painful SerDes to implement voltage mode driver instead of the traditional CMO driver. One more clarification is that actual power dissipation of the TX driver may also depend on several factors. For example, how is the output impedance control implemented? How is the design of the pre-driver, which may also add lots of extra power if not designed properly? How's the FIFO equalizer FFE implementation? The more complicated FFE is, the higher the power will be. With proper design, even though the power of the voltage mode driver is not really 1/4 of the CML, the ballpark power of the voltage mode driver could be 1/2 of the CML power. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback. and please share the comments down below. Lastly, please share the video link to the people who may be benefiting from it.